Okay. Well, good morning, everyone. Let's get started. We're in chapter 1110. We're going to be dealing with Maclaurin's and Taylor's series. 1111 also deals with them in a slightly different way. So I want to just get into this game. Let's start with question 2. Question 2, 3, and a couple others ask you just to write down the first non-zero terms. Okay. In this case, they want the first 4 non-zero terms. Now, we could do the power series, but we're only going to focus on calculating, the first, second, third, and so on terms. So the function that we're going to do it to is, in my case at least, is 9x e to the x, and it's going to be centered at 0, which is good because that's what Maclaurin series is. And if I find f of 0, the answer is 0. So I'm not going to count that one because they want terms that aren't 0. So this is going to be a pain in the butt. Do you recognize that you have to do a product rule here? So I'll call this f and I'll call this g, and let's see what we get. We get f dashed g plus f of g dashed. And that gets me 9 e to the x plus 9x e to the x, which if you put them all together, I know I could pull out the 9, but I'm not going to. We get our first derivative, and it looks like this. And the first derivative at 0 is 9 plus nothing times e to the nothing, which is a fancy way of saying 9. Now, if I want to get the second derivative, I'll do product rule again. So what will I get? I'll get 9 e to the x plus 9 plus 9x e to the x. That will become 18 plus 9x e to the x. And I get that fella is 18. And then I'm going to say, I am fed up differentiating. And I don't want to differentiate anymore. So I'm going to go looking for patterns. What do you think the value of the third derivative at 0 is going to be?
$27.
And it is. And what's the fourth one going to be?
36.
Can you see that we're using a pattern here to figure out? Have you noticed? Okay, maybe I should have done one more, but I think I could see it by the time I got to the, this guy here. Oh, look, the next one's just going to add another 9 on and so on. Now, we put that package together. We now have 4 non-zero terms, which is what they're looking for. If you take Maclaurin's, which is this guy, and you write it out without the sigma notation, and it's kind of helpful in these questions to do it that way, it looks something like this. Forever, right? It's a power series. Now, I know this guy is 0, but that guy is 9, that guy's 18, that guy's 27, and if I'd written the next one, he would be 36. So I should be able to say 9x over 1 factorial, 18x squared over 2 factorial, 27x cubed over 3 factorial, and finish with 36x to the 4 over 4 factorial. Of course, I have to make it look pretty. And so all I'm going to do on this next line is realize that 1 factorial is basically just 1, so that's 9x. 2 factorial, what number is 2 factorial? 2, right? So that gets me 9 as well. What number is 3 factorial?
6.
Right, so 27 over 6 is the same thing as 9 over 2. What number is 4 factorial?
24.
right? So 36 over 24 ends up being 3/2. Now, you might have to do some of them in your calculator, but what we've just written down here technically isn't f of x. Would you agree that it's just an approximation to it, because I'm only using the first, 4 terms, right? If I kept on going to infinity, right, if I did, the sigma version, wouldn't it be equivalent to f of x, right? Power series are the same as the functions they came from. And that's essentially how you're going to do this. So if you like differentiating lots of times, then you will probably have fun. Me personally, I do not like differentiating more than a couple of times because it's not hard to do, it just gets monotonous. Would you agree? As functions get uglier. So try and look for patterns to cut down your workload. If you don't see a pattern, you can still get the answer, but don't you just have to do every single differentiation, plug in 0, get what you get, right? Okay, next fella. Let's do 4. I was looking to see which ones, and I don't really feel like doing 3. This one, I think I can see a pattern, so I'm going to go for it. All right, we are going to do, what is it? We are going to do the general. Cool. Basically, question 4 and 5 are just the same thing in different ways. We are going to generate the entire Maclaurin's expansion of this guy. So, and it's 0. So I'll start with f of x, which is this fella. And the value at 0 is log of 1, which is 0. Very fair enough. First derivative, isn't it 1 over 1 plus 5x times 5? You happy with differentiating the natural log of 1 plus 5x and getting that? Now, if you plug in 0 in here, and well, that's basically 1. Oh, you just get 5. That wasn't too bad. Now, if I do the second derivative, if I differentiate this guy, you get 5 times negative 1 over 1 plus 5x times another 5. And you get, I know this is 25, but I'm going to write it as negative 5 squared. If you do the third derivative, and I'm going to tell you what the answer eventually would be if you evaluated at 0, you would get positive. Say again?
Wouldn't the one that's negative 5 squared, wouldn't that be f double prime?
This one here? Yes. Okay. If you did the third one, you're going to get 5 cubed times 1 times 2. I'll put little brackets around it. I don't need a number in the bottom. If you did the fourth one, and you found its derivative at 0, again, you're just going to have to trust me here. You get 5 to 4. It's going to be negative times 1 times 2 times 3. When you do these pattern questions, try not to calculate things. I know 5 squared is 25, but if you leave it as 5 squared, then 5 cubed and 5, 4, it's much more helpful. And you notice how this guy's 2, but I'm leaving it as 1 times 2, and this guy becomes, 1 times 2 times 3. The reason why it's a good idea to do this is that we're going to try to find this guy. Because once we find this guy, can't we just stick it in here and we've got the answer? So there is a lot of patterns going on here. Can you see it goes plus, minus, plus, minus? Forget about the 0 issue, right? Plus, minus, plus, minus. Agreed? It goes 5, 5 squared, 5 cubed, 5, 4. It goes, well, can't really see anything there. That's times 1 if you like. 1 times 2, 1 times 2 times 3. Okay. The first term especially is probably best ignoring. It'll come out in the wash, right? Just trust me, it'll work for this guy. And these ones, I think I can see a pattern, right? So let's work on if the first derivative gets me 5 and the second derivative gets me 5 squared and the third derivative gets me 5 cubed, would it seem reasonable that the nth derivative would get me that? Are you comfortable how I figured that one out? Now, how do we get this plus minus thing? We've seen plus minuses a lot. So how do you make a plus minus pattern happen?
-1 to the n.
Or -1 to the n plus 1, right? It's one or the other. I don't know yet because I haven't checked it in my brain yet. And what do you think it is, n or n plus 1?
Well, it starts positive, then goes negative. So I would say that it's n.
Okay, let me check it out then. Now, there are two choices, right? Let's pick n. Then the third derivative would be -1 cubed, which is negative. Is the third derivative negative? No. So isn't that not the right one then? Which means it's the other one. Now, the reason why you might have got out of sync is because this is position 0, this is position 1, this is position 2. So you may have been 1 out on your position counting.
Oh, I thought so. The position goes by not derivative. It goes by like the not derivative and then the derivative ones with position.
Well, no,
one being
this
not
you can call this n equals 0, n equals 1 if you don't like positions. Now,
right.
there's one.
I mean,
Mhm.
I mean that the n value is the number of times we've taken the derivative.
Yes, agreed.
So n equals 0 means we've taken the derivative 0 times. That makes sense.
Actually, that does make sense. I've never phrased it that way, but I like that way of phrasing it. Right. We still got one more guy to take care of. You can't really see it until you get to these two. The third derivative is 1 times 2, and the fourth derivative is 1 times 2 times 3. If I'd done the next one, can you trust me, it would be 1 times 2 times 3 times 4. Do you recognize guys that look like that? Isn't there a calculation or a thing that looks like 1 times 2 times 3 times 4 times 5, right? That guy.
Factorial.
Right. Now, which factorial are we talking about here? You don't just say n factorial, you got to put it into context. Do you notice that the fourth derivative is actually 3 factorial? Great. So what would the nth derivative be? If the fourth one gets you 3 factorial, the third one gets
factorial.
I think that's what I heard. N minus 1 factorial. Agreed. So you know, you sometimes have to tweak things. You know, each one's kind of got its own little uniqueness to it. Now I'm putting the whole package together now. N equals 0 to infinity. The nth derivative at 0. X to the n over n factorial. And we've got the guy that we need. So we should be kind of happy with ourselves. It's going to be -1 to the n plus 1, 5 to the n minus 1 factorial. And on the bottom, there's always going to be an n factorial, right? We should finish with style points. Can you see anything in this fraction here? Anything on the top that will cancel with somebody in the bottom? You do, don't you?
The
Did we
factorials.
forget an x to the n?
I did. Thank you. Right, I heard factorials cancel. After the battle, who wins and where does it go?
the n on
Right.
the bottom.
There you go. You have now generated the power series for that guy. You should be quite proud of yourselves. Can you see the amount of work involved in finding the power series for a function? It all revolves around being able to find the nth derivative at 0. Can you imagine that there could be functions out there where trying to find this formula would be virtually impossible because the function is so complicated? You know, if I said do the power series for x cubed sine x over e to the x all inside the big square root, can you trust me, if you tried to do a power series like that, you'd never find a pattern, you know, not an obvious pattern. So there are physical restrictions, right? Practical restrictions to getting power rules. So we don't tend to worry too much about that because we do the engineer workaround. Can't we just find the first 4 or 5 terms? And we know from experience that won't the first 4 or 5 terms be a pretty good fit to the function? At least close to 0, which might be all we wanted. So we don't need to get a perfect, you know, power series when just the first 4 or 5 terms will do. But very time consuming, as you can imagine, just in the amount of time we've done this. And I haven't finished, I just realized that. This is our function. And they are asking us for the radius of convergence, which is a lot better than the interval of convergence because that takes more time. Now, if you want to find the R value, the big capital R radius of convergence, don't we have to do a ratio test on this? So the limit as n tends to infinity of an plus 1 over an. And that's going to be the limit as n tends to infinity of all of these with an n plus 1 divided by all of these guys with an n turned upside down.
Wait, how did we just get a singular -1? Wouldn't it be negative? Okay,
Yes,
cool.
I'm just being careless. There we go. Try to make sure I don't put the guys in the wrong place. Okay, there's a lot of carnage happening in this question. Technically, there's an n plus 1 up here. Won't these guys cancel out and leave a -1 behind on the top? Agreed. Isn't -1 inside an absolute value just disappears? So I'm not going to write anything down. Technically, it's there, but it doesn't really matter that we ignore it because it's going to go away. These two cancel, leave me with a 5 on the top. These two cancel, leaves me with an X. And I tend to leave these guys alone for a while. Are we happy with this cancels down to this much cleaner looking ratio? Right, 5 left over and an X left over, both in the top. And then we've got these. These are considered constants. Would you agree that that becomes 1, a L'Hopital's rule? And so we're left with that. Now, for the ratio test says that this thing will converge when it's less than 1. And this will happen when the absolute value of x is less than 1. And that is the radius of convergence. So if you want to have a practical, what does this radius of convergence does is that if you're taking your function, right, your f of x, if you're keeping within, you know, 1 plus or minus 1/5, the function, whatever it looks like, and the power series will be a pretty good match. And then it'll probably start drifting, right? So it gives you a kind of ballpark place to be comfortable that the first 4 or 5 terms are probably going to give you a good answer, right? A good approximation, right? As long as you're only using range of x, in this case, between plus and minus 1/5. Okay, who should we do? Let's do Maclaurin's for cosine x. And, well, when it says Maclaurin's, that kind of means we're doing 0. No. Cosine x, the value of the function at 0 is the cosine of 0, which is 1. If you take its derivative, differentiate that guy, you get negative sine x, and the derivative there is negative the sine of 0, which is negative 1. This is negative cosine x. The value of this at 0, and I'm saying that is negative, that's 0. This is negative 1, that's better. If I do the third derivative of this guy, it becomes sine of x, and the third derivative at 0 ends up being 0. If I find one more derivative, get back to cosine of x, and the fourth derivative at 0 equals 1. Now, it's a bit messy, so I'm going to try and rewrite it again. Here is the list of the derivatives at 0. And this is a much more complicated list. What do you think the 5th derivative at 0 is going to be, and what do you think the 6th derivative at 0 is going to be? Just basically looking for patterns. What do you think the 5th derivative is going to be?
0.
And what do you think the 6th derivative is going to be?
-1.
Now, normally when we do patterns for the nth derivative, we try and find the nth derivative at 0. But sometimes that's really not easy or practical to do. In this case, I am going to find the 2nth derivative at 0. So I'm only going to find a pattern for the 2nd, 4th, 6th, and 8th derivative, essentially, right? Now, when you look at this function and you only focus on the even guys, do you notice that the pattern is quite simple? It's just 1, -1, 1, -1. Great. If I try to incorporate these zeros, can you imagine how difficult it would be to make a function turn 0 and then become 1, and then turn 0 again and then become -1? It'd be very difficult to try and do, so we'll avoid it. We'll find an easier way to do it. Okay, give me a rule for making plus and minuses, Sam.
-1 to the n plus 1.
Okay. Now, since we're doing 2n, can I just kind of adapt it and call it -1 to the 2n? Right. Now, that means we have two choices. right? Because we might get the plus minus out of sync, yeah. So let's pick one at random. Would you want fourth or sixth? Tell me which one to go for.
6.
6. So if I'm doing 6, isn't that 2n equals 6, right? 6 add 1 is 7. Do you agree this one works? That's the one that gets me the negative. Now we have to adapt this formula over here. And you might say, well, wait a minute, you're changing the rules. Not really.
Wouldn't that not work for n equals 4 though? The 2n plus 1?
This one here wouldn't work for which one? Sorry.
For the fourth derivative?
Fourth derivative is 2
Especially since 2n plus 1
No.
means that the answer is always going to be odd.
Oh,
so-
you're right. So we have to tweak this. How am I going to do it? Oh. Why don't you just call it n plus 1? So that would become 2 lots of 3. And that would get me 4. Oh, finally got it. It's going to be -1 to n. Okay, so the sixth derivative would have n equals 3, so that would work. The second derivative, the fourth derivative would have n equals 2, yeah, that works. The second derivative had n equals 1, that would work. And that guy's 0, and that one would work. Yep. That one was messy. Although I would have probably figured out I was wrong at the end. So the 2nth derivative is actually at -1 to the n. Now, my brain was thinking about this part of the puzzle. We now have to adapt this fella. Have you noticed that every second term is 0 and we only have even terms? So what I'm going to do is n equals 0 infinity, right? F to the 2n of 0, x to the 2n over 2n factorial. Are you happy that this sequence only uses the even powers because all the odd ones are 0? And we have this formula. Sigma n equals 0 to infinity. -1 to the n, x to the 2n, all over 2n factorial. And if you're interested, r is infinity. Okay, got a bit mixed up here with the -1s, but this is the power series for it. Thankfully, you don't get too many of those. Let me show you something remarkable. There's e to the x. This is cosine of x, and this is sine x. Let me write them down. if you look at these three very common functions and their power series, do you see anything that sort of connects them? Do they share anything?
Well,
Look
they're
at
just
E-
offset a little bit.
Yeah. If you made all of these positive and you made all of these positive and you added them together, wouldn't you get this guy? Now you look at e to the x, doesn't it zoom off to infinity? Doesn't sine and cosine just cycle? You would find it very unusual. I would have thought it was very unusual that this property even existed. Now, if you look at just cosine and sine and you look at the power series, do you see that the cosine function is only made up of even powers of x and the sine function is made up of odd powers of x? Can you remember way back in 141, we talked sometimes about a term called odd and even functions? And wasn't cosine even, right? Y-axis was an axis of symmetry. And was it the sine function odd because it had half-turn symmetry? Were you ever curious why they were called odd and even functions? Why they didn't have some other name? Well, if you take a power series of a function and it's only made up of even powers of x, it will be an even function. And if you take a power series of a function and it's only made from odd powers of x, it doesn't need to be all of them, but they're all odd, right? It's going to be an odd function. Does that kind of make sense now when you see that name? The odd and even functions are actually a reflection of what the power series is like. I think that's kind of cool. What do you think the power series of sine x plus cosine x would look like? Doesn't it look a little bit closer to e to the x? What you're looking at here is the fundamental structure of functions, right? It's a bit like you take a function and you take an X-ray of it and you look to see what its skeleton looks like. Because what you tend to see is the surface of a function, what it looks like, superficially. But when you really analyze what does a function look like inside, what does it look like from its power series? It's so much more interesting. Cool stuff. Right, let's move on. Let's try to generate some more Maclaurin series. And I've got time, I hope, to do two. So first one I'm going to do is 2 to the x. So jump right in. If you differentiate 2 to the x, don't you get 2 to the x times the natural log of 2, which I'll just stick at the end. If you do the second derivative, don't you get 2 to the x times the natural log of 2 times another natural log of 2? And if you do it a third time, you will get 2 to the power of x times the natural log of 2 cubed. The value function at 0 is 1. The first derivative at 0 is 2 to the power of 1 log 2. The second derivative at 0 is 2 to the power of 1 times log 2 squared. And the third derivative at 0 is, I'm calling this 2 to the 1s, 2 to the 0s, my apologies. 2 to the 0 times the natural log A2 cubed. So if you want to find the nth derivative at 0, would you agree it's 2 to the power of 0 times the natural log of 2 to the power of n, and 2 to the power of 0 is 1, so you get the natural log A2 to the power of n. Didn't that come out really cleanly? I know I'm very fast, but I've kind of short of time now. Be comfortable about that? After 3 or 4 derivatives, you see a pattern. So Maclaurin series, n equals 0 to infinity, this guy. Everyone looking good? Okay, let's get the other one out the way then. That will work for 8 to the n and 10 to the n. Want it as well? Okay. And who's the other guy? I had him a minute ago and lost him. Let's do f of x of e to the 3x. Power series for this fella. Well, that's e to the nothing, so that's 1. First derivative, 3 times e to the 3x. First derivative at 0 is 3. Second derivative, 3e to the 3x times another 3. Do you think we can jump right to the nth derivative on this one? What would the nth derivative be in this
3 to
story?
the n.
3 to the n. And so the Maclaurins is n equals 0 to infinity, the nth derivative at 0, and x to the n over n factorial. They're not too bad. You agree 2 to the x's and e to the 5x's aren't too bad, right? Nowhere near as horrible as the cosine or the sine was. Okay. Let's do Taylor series. At least start it so tomorrow we can work on it. What the guy Taylor discovered is that you can do a power series centered at A, and the formula for it is the nth derivative at A, x minus a to the power of n over n factorial. And we say that this is centered at A. And when you write down a power series in this form, we call it a Taylor series. And when you look at Maclaurins and you look at Taylors, would you agree that Maclaurins is just a special case of Taylors? Isn't it just Taylor centered at 0? And there's a number of reasons why we want to use this fella. He's a little bit more clunky, a little bit uglier to look, you know, to find and to look at, but he is useful. One of the reasons he might be useful is, can you imagine that the original function had a problem at x equals 0? Maybe there's a vertical asymptote, you know, like 1 over x, right? Bad news, because you couldn't find derivatives at 0, right? There'd be 1 over 0 infinities everywhere. But if you move the center to away from the bad number, like maybe center it at 1, couldn't you get the power series for the function, but shifted? Right. If you want to do the power series at, suppose you had a function and you wanted to evaluate it at a number like thousands, right? X at 1,000 to 2,000. If you did this Maclaurin series, do you know you'd have to use literally hundreds, if not thousands of terms to be accurate because you're so far away from zero, right? It's really good at zero and not so good further out. So you need many more terms to be good further out. Well, you could do a Taylor series at X equals 1200 if that's what you're interested in. And that would give you a nice approximation to the guy you're looking at. And you wouldn't need hundreds of terms. Couldn't you just get by with the usual 5 and that's good enough? So try to justify why you might want to do it. So let's show you a very simple question. Question 9. In fact, this question is so simple, you might talk yourself out of using it. Okay. If you can find the nth derivative at a, in this case at 8, isn't the power series just going to be n equals 0 to infinity, this guy, you might say why 8 because it's centered at 8, a is 8, all over n factorial. And keep your eye open for, oops, I forgot some terms there. So that is this mess. That n factorial kind of ended up in the middle. Is there any style points that you can do? So if I take that guy out, can you see that's Fn of A? And there's n factorial in the bottom. Any style points?
You can cancel out the n factorials.
And if you can, you should. And there's your power series, centered at 8. So it's going to have a lot of similarities to the Maclaurin series. Can you imagine you're going to get questions where you find the first 4 terms? So you just find first, second, third, and fourth derivative, but at 8. And you just plug them in as normal numbers. And more difficult one is to generate the entire power series. And for those, you're going to have to figure out how to get a formula for the nth derivative, instead of at 0, the nth derivative at 8 or 2 or whatever the center happens to be. And I think that's a really good place for us to finish. So say your last name and bye-bye. I'll hang about for a question.
Alrighty, I got a question.
Oh, I got a question. Go for it, Tim. What you got?
Hang on, I'm finding it. Just give me a minute.
No problem.
It's the same one I asked you last night. I ended up figuring it out, but
Okay.
I'd really like to run through it one time. I'm just gonna go pull it up on my camera gallery. So it was find the power series representation for the function, and then it was f of x over 2 plus x squared plus 1.
F of x equals
X over 2x squared plus 1.
okay. So you're going to pull out an x and you're going to call it, I like to write them that way around. It's just me, right? You're going to get that. Agreed?
Yep. I didn't struggle with this part, and then I went and I looked and I said, oh man, this looks like then it's the one that has -1 to the n, and then it's x. I think it's x to the n or something.
That guy, right?
Yeah. Now,
Okay.
where did the 2 go?
It doesn't go, it's there. Oh, 2, sorry, that 2. Yeah, I missed it. It's there. Little tiny guy, but it's there. So let's expand it a little bit. Great.
Yep. Yep. I
Now,
totally
let's-
agree.
Right, let's bring this x inside. This is, I think, where your problem happened.
Yeah. So that x comes in and it becomes x to the n.
No, it doesn't. That's your mistake. It's x,
Uh,
and it's still x. Whatever this is, in this case it's x, but maybe next time it's 2x or 5. When you bring it inside, it's still 2x or 5. There is no attached power to it. In fact, you shouldn't have an x to the n outside, because anything that's got an n isn't allowed to be sucked out. So there's no way it could have been an x to the n anyway. It would have to be just a fixed value, in this case x to the 1. And when you bring a single x in, it's still a single x, and it joins 1 to the power.
so how I figured it out is I brute forced the hell out of it. I knew everything except the exponent of x, and then I integrated it, and I knew what the value of the integration would be, and then I did that along multiple points, and then I used that to go back and find out what the power should be.
And did it work?
I did in fact get the right answer doing that, but it was not pleasant.
Are you happier with the less rigorous way of doing it?
Yeah, absolutely. I just could not for the life of me figure out what the I see now that I was making it x to the n, and so then I was getting x to the 3n, and then that wasn't working. And I did get that answer, but I just did it in the least pleasant way possible.
Rosie, you have a question or a comment?
Yeah, could we go over number 3 on 11.8 part B?
1.8. Number 3, part B. Is it something you could read to me, or we'll have to go looking for it?
I could read it to you.
Okay.
So series from n equals 1 to infinity of the square root of n over 8 to the n power
Okay.
times x plus 6 to the nth power.
So something that looks like that.
Yes.
So this, to me, this is a Taylor series centered at -6, but you're probably not interested in that. What was the question? Radius and interval of conversions?
Yes.
Okay, so we need to go and do the limit as n tends to infinity of an plus 1 over an. It's going to be a little bit clunky, this thing, because it's got lots of bits. That's going to be the square of n plus 1. That's going to be 8 to the n plus 1. This guy's going to be x plus 6 to the n plus 1. Then you turn everybody upside down, you're going to have an 8 to the n, a square root of n, and on the bottom, an x plus 6 to the n. So there's going to be a whole load of this cancelling out with that kind of thing going on here. If I take this fella and cancel it with that guy, there's an 8 on the bottom. If I take this power and that power, they cancel out, and that's going to leave me a single x plus 6. I'll be happy about those two cancels.
Yes.
Right, and I just realized my square root of n's in the wrong place. It's down there, right? And we're left with some stuff with n's in it, right? Now, this fella here is going to have a limit of 1. But let's try and prove that it's got a limit of 1. So, was that your issue? Not being able to get this, or were you okay with this?
I had a hard time getting to this point.
Right, so are we okay with the ratio test and the cancelling now that you've seen
Yeah.
it? Okay,
That's
so
good.
let's focus on just this piece here on its own. And there's lots of different ways of tackling this. This is just one of them. What I might do is I would look at that and I say, wait a minute, they're both square roots, so I'm really trying to do that. And wait a minute, I can pull out the square root and just do this. And this is dead easy. This is 1, so it's the square root of 1, which is 1. So that's how I would prove that the limit of this as n tends to infinity is just the number 1. Now, that makes this fella times 1. That makes the limit equal to that. Are we good still?
Yes.
Right. Now, for a ratio test, the limit, whatever that limit happens to be, needs to be less than 1. But we also have to make sure that our answer is going to be in terms of x, or in this case, x plus 6. So I'll multiply both sides by 8 to get this relationship, right? It's the same information as this, but it's written down in a format that we need, right? That the absolute value of x plus 6 needs to be less than 8. And I have now found the radius of convergence. It's 8. Now you want to do the interval of convergence. You take this and you rewrite it without the absolute values. I call that sandwich. If you take 6 away from both sides, your interval of convergence then are values of x somewhere between -14 and 2. And then you test the 2 endpoints to see if any of those two make a difference. If I plug in 2, I get 8. That cancels with that. The square root of n is divergent, so nope. If you plug in -14, you get -8 to the n. -8 to the n cancels out 8 to the n, and you're left with -1 to the n, square root of n, but that's just equally as bad, so that's another no. So the interval of convergence stays put as curved brackets, so you can't use me, -14 to 2.
Okay, thanks for explaining that. Also, I wanted to go over my test, which I
That's
realize you can't do right now.
we can do that during office hour. That way it's just us, okay?
Okay, I'll go to office hours.
Right, I'll see you there maybe in about a few minutes.
All right.
Okay, Tim, you get any questions? Christian, you get any questions? Tim, 2 thumbs up, he's good. Christian?
Oh, I always stay on all your examples.
Not a problem.
I do exactly the same thing.
People.
I will say it was super fun to go through and like actually find the value of integrals that you can't find normally. So a guy that did like the sine of x to the 4th. He calculated that integral to like 12 points of precision. That was pretty cool. 12 decimal places of precision. I mean,
Well, you know,
nice.
many advantages, but if you can find the power series, even if it's only the first 5 or 6 terms of a power series, most of them, the large percentage of information is already contained. But a power series is just a polynomial, and polynomials are very easy to integrate. And so you can get to 12 decimal places or 20. You know, you just need more terms if you want to be more accurate.
As an engineer, that's the part that really interests me. You know, not actually doing the math is the use of it as an approximating tool.
We are total opposite ends of the spectrum, but I do understand your viewpoint. I like the math part and not the number crunching part, and you like the number crunching part, but I can understand.
Figured
that.
out how to make Excel do it for me. So, all right.
Right, perfect.
I appreciate
Okay.
it. Have a great
No.
day. Thank you.
You're welcome. Bye-bye.